with me. Well, good afternoon, grade 12s. I hope you have the assignment done for today because, it was due today. It's supposed to be in the folder. And I'm kind of disappointed that a lot of you don't have it in there. Let me check Amy's homework. Just up to lesson 3, Amy. That is very disappointing. Extremely disappointing. And no worksheets? What is going on, Amy? I don't know. Not impressed. Actually, I'm just kidding. That's April Fool's. But, all right, Wiltley did legitimately ask a question. And there is a couple of questions that have some unfinished business on this two-dimensional worksheet. So this is like the worksheet we did on conservation of momentum, not on energy, okay, the one that we just did. Let me talk to you about question number 5 and also number 4. This business of whether or not the collision was elastic. Now I think I mentioned to you how you work this out before. It's probably somewhere here in the margin. Oh no, it's not, but anyway. But let's just go ahead and look at question 5. Okay, and let's answer both of these questions. Number 1, letter A and letter B. Okay, so this is the penguin question. And you should be doing both question A and B. Now that I've taught you about kinetic energy, you're able to answer this question here, elastic or inelastic. And just let me explain that to you. Before we look at this question, actually, let me explain it to you. And I'm actually gonna make a separate note for this. So let me do it right here. Okay, elastic and inelastic. And I'm just going to say here, and partially elastic. All right, so here's the deal. Okay, what's up with this thing of elasticity and collisions? Well, if you had like a really elastic ball, see, what does elasticity mean? Elasticity means, okay, let me define elasticity for you. Okay, elasticity is the tendency of an object to reform its shape when deformed. Okay, so let me give you an example. A rubber ball. Whoops, what am I writing there? A rubber ball. Is it elastic? Well, yeah, it's fairly elastic. So in other words, if you squeeze a rubber ball and sort of just let it go, it sort of returns to its original shape. And that's what makes it bouncy. Okay? A rubber ball, a spring. Springs are elastic, so you stretch them or you compress them and they reform to their original shape. What else would be a good example of something that's elastic? Anything stretchy, anything made of rubber, okay, like a rubber band, is also elastic. Okay, you stretch it, it reforms its shape. Let's talk about these items are elastic. Okay, items that are inelastic. Let's say dough. Okay, dough is inelastic. What else? Putty, like silly putty, would be, well, silly putty has some elasticity, to be honest with you. You roll it up into a ball. But generally speaking, putty like clay, let's say, tends to be inelastic. In other words, if you throw a ball of dough on the wall, does it bounce off or does it stick to the wall? So anything sticky tends to be inelastic, okay? So now this is not a black and white concept. Like, it's not either it's elastic or inelastic. Most things well, here, actually everything is partially elastic. It's just that these items here have a very low elasticity, if that makes sense to you, and these items here, so this is low elasticity, not zero. After all, a ball of dough does reform its shape a little, okay? When you're trying to roll it out, and it sort of rolls back in on you a little. And here, these have a high elasticity. Now, why does this matter in collisions and stuff? What does that mean? Well, when two rubber balls sort of hit each other and bounce off, they reform their shapes. And in the process, you get a lot of kinetic energy that stays in the system as a result, okay? So here's the thing, with collisions, when you're doing the math, collisions go like this, okay? If the EK, sorry, let me mute my notifications. Here, I'm just going to say number one, momentum is always conserved, okay? In isolated systems, okay? With no external forces acting on them, okay? Number two, so that's regardless of whether the objects are elastic or not, okay? So I'm going to underline this word, always, okay? Number two, EK is conserved for what we call perfectly elastic collisions. Okay, so let me try to explain that to you. It has to be perfectly elastic, and actually in real life, in the real world, whoops, this never happens. But it can almost happen. You can get an almost perfectly elastic collision. Like for example, when two atoms collide, they can be nearly elastic. And so sometimes we do the math because it works out, okay? It pretty much works out. So to a good approximation, it's nearly elastic. So perfectly elastic means both kinetic energy and momentum are conserved, okay? So here's the thing. I'm just gonna, in order for you to answer those questions, I'm just gonna recall, okay? Momentum, P1 plus P2 equals P1 prime plus P2 prime. This is number one, right? Momentum is conserved. Now number two, you have this. Oh, actually, hang on. Before I do number two, let me write it out this way. M1 V1 plus M2 V2 equals M1 V1 prime plus M2 V2 prime. Okay? Now, these are vectors. Okay? And this is a vector equation, so it's vector addition. But kinetic energy is not a vector, it's a scalar. So number two, what it means is the EK before the collision would equal the EK after. Okay? So what that looks like is 1/2 M1 V1 squared plus 1/2 M2 V2 squared equals 1/2 M1 V1 prime squared plus 1/2 M2 V2 prime squared. They could never stick together, okay? So this one is, this equation number two, you can only use it if it says it's perfectly elastic, but you're not going to get any questions like that just yet, okay? So like those questions are coming later. But how do you tell if a collision is elastic or not? Well, what you do is this is the total before the collision, right? And this is the total after. So what you just do is you check to see if they're equal. Usually they're not. Usually there's less after. And what's happened is you've lost some to waste heat. Okay? So in an inelastic collision, In an inelastic collision, the EK that's lost to waste heat, which happens all the time, will equal the EK before minus the EK after. Okay, so in other words, there's some energy. Let's say you had 100 joules of kinetic energy in the system before the two objects collided, and let's say you have 65 joules after. Well, that means you lost 35 joules to waste heat, and normally you lose something. Okay, but if they stick together, you lose the most that's possible to lose in the system. Okay, so an inelastic collision, the word inelastic means you have the maximum loss, and that means they stick together and have the same final velocity. Okay, and that's the definition of an inelastic collision. All right, so now that you've seen this information, let's go ahead and do this question that's on here. Okay, so the question that's on the worksheet. Okay, the question that's on the worksheet looks like this. Let me go back to it. All right, the penguin question. Okay, so this question, if you do question number 1, okay, it says a 15 kilogram pot is waddling east at a velocity of 7, collides with a stationary 10 kilogram. Afterwards, the 15 kilogram penguin is traveling at whatever. Okay, so what you do is you set up your table. I'm going to pick south and east. Okay, and so the initial momentum of the 15 kilogram penguin is due east, and it's 7 meters per second and 15 kilograms, right? So that's 7 times 15. The other penguin is 0. And so this is, if you like, P1, and this is P2. Now I'll put our yellow line. Okay, and we look at afterwards, it's 4.2 meters per second, 20 degrees south of east. So you're going to go like this. You're going to go 4.2 meters per second. So this is P1 prime. 4.2 times 15. Okay, so it's mass times velocity. Times the sine of 20. Okay, and then P1 prime on the east side will equal 4.2 times 15 is the mass times the cos of 20. And then what you do is you're going to solve this for P2 prime. Okay, the other guy's mass is what? $10 kilograms. Okay, so it's going to be 10 times V2 prime south, and this P2 prime east will be 10 times V2 prime east. Okay, so anyway, I will let you deal with answering this question. Okay, just solve for the components as usual and solve it for V2 prime south. Okay, and V2 prime east. You're definitely going to get that the south one is negative, so you're going to get something that's north. And here the east one may be negative, it depends. 7 times 15 is quite large, so it may not be a negative number. All right, so that's how you get the answer to the question. Oh wow, where is the answer to the question? North of east, yeah, okay. Let's assume this answer is right, okay? So let's not waste our time. You know how to do the rest of the component method. So this is question 5, okay? And this is part A. Okay, so A, you get your answer and you find V2 prime, whatever it is. And let's say the answer is 5.1 meters per second, and it's 25 degrees north of east. All right. Okay, so now here's the deal. What about question B? Is it elastic or not? Well, let's find the EK before. Okay, and the way you do that, I'm sorry, that's a K. K before. The way you do that is you're just going to total it up. So it's just one penguin moving, so it's going to be 1/2 m1v1 squared. The other guy is 0, right? So just taking out my calculator, that is, what's his mass, 15? So that is 0.5 times 7 times 15. Oh, I'm sorry, I got that wrong. Wait a second, what's his original speed? 15, 7 is his speed, 15 is his mass, right? So 0.5 times 7. Gosh, I'm dumb. Okay, so 0.5, 7 is his speed, right? 0.5 times 15 times 7 squared. I get 367.5 joules. So this is 367.5 joules, right? Now the EK after, when they're both moving, whoops, that is equal to 1/2 m1v1 prime squared plus 1/2 m2v2 prime squared, like that. And we can totally ignore the direction. So these are scalars, right? So the direction doesn't matter. All right, so one penguin, let's do the first one first. So it's going to be 0.5 times his mass is 15, and his speed is 4.2 times 4.2 squared. I get 132.3 joules plus 0.5 times 10 for the other guy, his mass, and his speed is 5.1, so times 5.1 squared equals 130.05. So I'm going to add that to 132.3, and I get 262.35 joules. So combined, yeah, all right. So like if you look at it, if you take these two energies, then we clearly see that there's more before and some has been lost, okay? So therefore the EK that's lost is equal to 367.5 minus 262.35, like that. So let me work that out, plus 367.5. I get 105.15. And that's how much was lost to waste heat. I remember when we did this question, it was on the practice quiz. So therefore, it's partially elastic and it's inelastic. Like you've lost, I don't know, about 1/3 of the energy that you started with, maybe a little less than 1/3. So, and you've retained 2/3 of the energy. Okay, but some of the kinetic energy was lost, and therefore this is an inelastic collision. Now, they didn't stick together, otherwise they'd have the same final velocity. But I would say that technically you would say it's partially inelastic, okay, or partially elastic, whatever. So you did keep some of the kinetic energy, so they kind of bounced off each other. So there was some elasticity there, but it's not perfectly elastic, which means some of it was lost. All right, that's it. So that's how you do question 5. And that is how you would do any question like that where they ask you whether collisions are elastic or not. So that's it for today, and enjoy the rest of your night.